So question 2, we've got races, so results shown in table. X is the number of years from the beginning of 2060 to the end of the time period. So beginning of 2060 to the end of 64 is going to be 5. So we've got X is 5, 10, 15, 20, 25, 30, 35. And we've got Y is the fastest time in seconds. So in a moment we're going to need to convert those. We've got an equation like this. Those are constants. Okay, so we start first off with Y equals AX to the power of B. We know what we're aiming for. So they've given us a fairly nice hint there. So we can learn both sides. We can then separate them. And then we can bring the power down. And that's it. Okay, so for part B, they've very kindly worked them out into the number of years and the number of seconds for us. And then in a second we'll just have to plot it. So if we go into table function, and I want that to just be ln x, not ln x minus something. And so first off I want 25. So that'll be 3.22, 30. So that's 3.40 and 35, which is 3.56. We then need the y's, so we've got 7, 8.4, which is 6.66. We've got 8.4, which is 6. To 4 significant figures, which is, so we actually need to read the question a bit more carefully. So that is 6.660 and 6.657. And then lastly we've got 777, which is 6.655. Okay, so we've then got a graph to plot and a line of best fit. So each little one is worth 1. So 6.70. These are going up in 0.2s, so about there. And we're on 6.1, so that's going about there. 2.3 is going up to 6.680, so that's there. 2.71 and 6.67 is halfway, and then 6 will take it to about there. And 3 dead on, and 6.67 is there. 3.22 and 6.66. This one is looking like I might need to check it in a second. 3.4 is 6.657 and 6.56 is coming in at 6.55. Right, so I need to just double check the one at 3. That was at 6.67. No, that's right, it just looks a bit low. Okay, so drawing a line of best fit. Your line of best fit is going to be slightly different to anyone else's, but there'll be a sort of range as to what they'll accept. So if we use a ruler that's actually straight, that looks close enough. So that's cutting there at 0.2, 6.744. So we've plotted it, we've drawn our line of best fit, we've then got to estimate A and B and then express X in terms of Y. So if we go back to our previous thing, we had Y equals AXB, and that became ln Y equals ln A plus B ln X. So we are going to need to find our y-intercept. So we know that that's 2D. We know that ln A is our y-intercept, and that is 6.744. So to find A, that will be e to the 6.744. So E 6.744. So we've got a value of A, that is 848.9. Which, looking at it, is reasonable given what's on our table. And then we need our gradient. So the 2 points that we can use for our gradient would be 0, 6.744, and a second point, we'll take the 3.22. So that was 3.22, 6.66, and to work out our gradient, which will happen to be B, that'll be the change in Y, so 6.66, take 6.744 over the change in X. So we are expecting a negative gradient on the basis it's going down. So 6.66 minus 6.744 over 3.22. And we have a gradient of 0.0261. And then we need to substitute this into our original equation. So we have y equals 848.9 x minus 0.0261. Okay, part E. So 2014 is 20 years after that, which means our x value will be 55. So x is 55. So if we put that into our model, we've got y equals 848.9 55 to the power of minus 0.261. So 848.9 times 55 to the power of minus 0.0261. Ooh, there's too many fives in there. So that is 764.6. And at that time, the fastest time was 12 minutes, so that's 60 seconds, and 46.8. So 12 times 60 plus 46.8, that equals 766.8. So it's pretty close. She's about 2 seconds out. So I'll accept that. So the time is consistent as she is less than 3 seconds out.